Hello everyone, my name is Marco Lovato. I'm master student at ProMech, which is the graduate program in mechanical engineering of the Federal University of Rio Grande do Sul. I'm glad to be given the opportunity to be here presenting to you the first outputs of this research beside Adriane Prisco, my advisor and coordinator of NIPI, which in English means Wind Energy Studies, Research and Innovation Integration Center. One of our objectives with this research is to stimulate the development of strategies for delivering high-fidelity references for the improvement of low-fidelity models, which are also called engineering models for large multi-megawatt horizontal axis wind turbines. High-fidelity references may be either experimental data or also full 3D computational fluid dynamics simulations. And low-fidelity models or engineering models include, for example, the blade element momentum and Vortex Wake Models. Such low-fidelity engineering models are very important for delivering fast results in many applications. However, in order to be properly built, they must be based on reliable data, representative of the true physical phenomena that's going on. The data used to calibrate physical models of any kind usually come from high-quality experimental campaigns, such as the ones performed on the Mexico and the New Mexico experiments over a 4.5 diameter wind turbine-type rotor. But what about the large multi-megawatt horizontal axis wind turbines? Well, currently there is no experimental data available, mainly because its acquisition under controlled conditions is impractical. Indeed, as of the author's personal opinion, the real flow phenomena occurring in huge wind turbines is currently much closer to be fully understood by the application of CFD than by experimental campaigns. Our research is therefore a contribution to the quest of the CFD strategies better fitted to this, to correctly capture the complex flow phenomena intrinsic to large horizontal axis wind turbines. The CFD modeling evaluated in our research here have three main characteristics. First, it solves a compressible flow in order to address the Mach numbers greater than 0.4 that happen near the blade tip of the Mexico rotor. Second, it used a turbulence model that is tailored for the intrinsic anisotropic features of turbo machinery flow. Third, is Mach converged according to the Grid Convergence Index study proposed by Chalik. As of our outputs, besides delivering blade pressure loads that are comparable to the New Mexico experiments, and also to other CFD studies on the same case, this research delivers an information that we did not find in the literature around the Mexico campaigns, which is the blade thrust and torque obtained by continuous integration using the CFD mesh resolution, and including skin friction. Indeed, forces on the blade, including the wall shear stress, may not be very practical to be gathered experimentally for the rotating blades. And we expect that the thrust and torque values that we offer here from the CFD analysis may be considered closer to the physical reality of the Mexico rotor under its design speed, and thus a possible reference for the calibration of low-fidelity wind turbine engineering models. Now I'd like to show you how we set up the blade geometry and the computational domain for this simulation. The Mexico rotor is a three-bladed rotor, and the virtual geometry of a single blade was placed inside a 120-degree periodic computational domain. This periodic computational domain is composed by a rotating region, in yellow, which is surrounded by a static region, colored in gray. The free stream airflow enters in the dark red surface here and exits the domain in the brown surface. Regarding the physics setup, the airflow was modeled by a fully turbulent, compressible, and steady-state Reynolds average Navier-Stokes. Density was modeled as ideal gas, and for dynamic viscosity and thermal conductivity, the Sutherland's law was used. Regarding the turbulence model, we used the elliptic blending Reynolds stress. A literature research suggests that this is the first work to assess this turbulence model on a wind turbine type rotor with mildly compressible flow region on the blade tip. Reynolds stress models are already known to be capable of resolving the anisotropies of rotating systems, but this newer RSM, called Elliptic Blending RSM, has an extra layer of fidelity: its low Reynolds modeling capabilities, making this RSM appropriate for modeling flow separation and reattachment, which is very important for turbine machinery. This figure depicts the suction side of the blade tip. Here we can see three data. First, a mesh slice at 92% of the rotor radius, which is colored by the Mach number, where Mach numbers as high as 0.4 are attained. Second, the mesh on the blade tip surface, colored by the wall Y+, which is kept below 2 everywhere. And third, the Q criterion rendered on the volume to identify the blade tip vortex. Well, the majority of the CFD studies found in the literature on wind turbine rotors do not model a compressible flow, but employ the incompressible formulation instead. Even though compressibility seems not to play a crucial role on the overall static blade loads, some studies do suggest that it should not be ignored when some particular aspects are of interest, namely the blade tip vortices, aeroelasticity, and aeroacoustics. In the paper, we invite you to take a closer look on how our results compare to the experimental data and to other CFD data at 5 different sections of the blade. But here, in this presentation, we'd like to focus only on the integral loads. Here on the left, you can see the torque values for one single blade, and on the right, the thrust values. In gray, we have the experimental values. In green, the averages from the CFD literature. And in red tones, the values from our research. As you can see, our results are similar to the experimental and to other CFD data when integrating only the 5 discrete sectional loads and excluding skin friction. But we also deliver here our results considering the complete blade surface, using the mesh resolution and including the wall shear stress. As a conclusion, our research not only proved the ability of elliptic blending RSM to deliver blade pressure loads comparable to the experiments and to other CFD studies on the same case, but also delivered integral blade loads data that may be valuable for the low-fidelity modeling scientific community. The complete dataset of the simulations we performed is downloadable from a link that is provided in the paper. We'd like to give a special thanks to the consortium that performed the Mexico measurements, and to all the researchers that devote themselves to numerical analysis of wind turbines, to whom this research is also dedicated to. I'd be happy to go after the answers for the questions you may have now or any time in the future. Thank you very much.